move on to our next presenter, and that's Bryon Czarnik. He'll talk to us about football and astronomy, the making of the Giant Magellan Telescope mirrors. Over to you, Bryon.
Okay, thanks, Paul. We're entering Super Bowl season. In fact, next week is what some call the Super Bowl of Astronomy, the annual, this time virtual, meeting of the American Astronomical Society. And a few weeks after that is the other Super Bowl, the one to do with football. Now, the people on this image here, the players, they're not in the NFL, but they are players in the University of Arizona Wildcats in Tucson. And these people, they play out of this huge stadium that holds well over 50,000 people. And you'll see on the east side of the stadium there, the Richard F. Karras Mirror Lab. It happened to be the only available space on the campus to put a giant mirror lab. And this lab is responsible for making the world's largest telescope mirrors. The maximum that they think they technically can make these days is 9 to 10 meters across. And the ones for the Giant Magellan Telescope that I'm talking about, they are 8.4 meters across. Now, a year ago, I was fortunate enough to visit. Most weekdays, they give tours for an hour and a half of the facility. It's a 3-story building with 4 large halls in it. The building itself is separated from the grandstands so that the stamping of feet and roar of the crowd don't upset the delicate operations. And the whole building apparently floats on some giant airbags. There's 4 facilities in this lab. The first one is the furnace area. It's a 40-foot diameter rotating furnace. And the next area is a large 3-story integration hall for working on the mirrors. Next to that is a 28-meter high optical test tower. And of course, the last lab is the polishing and grinding facility. The lab is large enough they can actually work on 3 of the mirrors at one time. And each mirror, each 8.4 meter mirror, takes approximately 4 to 5 years of work to complete. Now, you have here an image of the GMT. It's in the Las Campanas Observatory, not far from the twin Magellan telescopes in the southern Atacama. Work on this began about 2 decades ago. And one of the first orders of business was to make sure that they could successfully make optical quality primary mirrors to the spec required. So that work began 15 years ago. And the entire observatory should be completed by 2029. This map of Chile shows where the major observatories are in Chile, and I've circled where the Giant Magellan Telescope is. You can see south of there the LSST, now called the Vera Rubin. And to the north, you have the Atacama array, and what will be another extremely large telescope, strangely enough, called the European ELT. So here are cutouts of the Giant Magellan Telescope. On the left, you see the inside. The building itself is actually 22 stories tall. That's 63 meters. And if you were to put that building at the base of the Horseshoe Falls, it would stick above those falls by another 15 meters. It's that large. And it's just a massive, massive structure, weighing about 6,200 pounds for the telescope and the pier, which happens to be about half the weight of the Brooklyn Bridge. Yet, even though it's so large, it can rotate 360 degrees in 3 minutes. You can see on the right-hand side that the primary mirror is made up of 7 8.4 meters, 8.4 meter mirrors in a parabolic shape for a total of 25 meters in diameter. The primary is very fast, f.7. They're trying to achieve a resolution of 0.02 arc seconds. You can't see it that well here, but the structure above the primary is holding a secondary mirror. There's 7 of those, and each one is paired with the corresponding primary. They are only 1.05 meters in diameter. The Giant Magellan Telescope is 10 times more sensitive than the Hubble Space Telescope and 4 times more so than the James Webb scope. It's like it would be capable of seeing a dime, from the face of the dime, the detail of that from 100 miles away. So extremely excellent resolution. And paired with something like the JWST, there should be fantastic discoveries in the next few years. Just want to go back a little bit on history, and Chris showed this scope. This is the Mount Palomar Observatory and the Hale Telescope. On the left, you can see the 200-inch mirror of the Hale Telescope. That's about 5 meters. Now that mirror is made out of Pyrex glass, just like the Pyrex glass in the David Dunlop Observatory in Richmond Hill here in Toronto, which is only 1.88 meters and weighs 2 tons. This particular mirror weighs 20 tons after several tons was ground off it. It's made out of the Pyrex glass, which is borosilicate. And the reason being, they tried to make a very stiff mirror out of fused quartz, but GE wasn't able to scale it up. Turns out that Corning Glassworks in New York was able to do it successfully after a second try. And the mirror was done. It was shipped to California. And after about 13 years, a little bit of interruption because of the war, the telescope was done in 1949. So for 40 years, this was the largest telescope that could be made. It was the king of the scopes. Any larger, there would be problems with gravitational sag, the cost would get enormous, and the time to make the telescope would be excessive. So how do you solve those problems? A professor at University of Arizona came up with a couple of solutions with his colleagues. One of them is to, instead of have just these 36 holes in the Hale telescope, he would make a very comprehensive honeycomb, much as the bees do in nature. It would be very rigid, as a honeycomb is, and the weight would be reduced by 80%, whereas in the Hale telescope, weight was reduced by only 50%. So he made a kiln in his backyard in Tucson and got some custard cups and some Pyrex dishware and melted it to make a sample, and he was successful. However, his wife was not a science experiment in the backyard, so they found space in an abandoned synagogue near the campus and set up the first mirror lab there. Now, the second innovation that he and his team came up with was something called spin casting. So just as in this glass, when you spin the liquid, you get a parabolic shape, which is ideal for mirrors. And you couple that with a mold that is a parabolic shape, and you can save a lot in the cost of the glass and in the time it takes to grind the mirror, because you're already starting with a parabolic shape. So this is what they did. Now, they managed to eventually find that space under the stadium and built a large mirror lab that you saw in the earlier picture. This is an image of the central mirror segment of the GMT, with all the people that worked on it sitting around. It's just come out of the oven. You can still see the hexagonal ceramic cores that make the holes in the back of the mirror throughout the structure. The mirror itself takes, as I was saying, 4+ years to make, longer depending on what else is going on. Making the mirror blank is 3 months of effort in the furnace. Then there's the matter of cleaning off the back of the mirror, and I'll show you that shortly, and then polishing the rear surface completely flat and attaching a structure for active optics. And finally, you get to the key part, and that's grinding the front. So a rough grind is done by a large optical generator, and a fine polishing occurs for a process that takes a year or even longer. This cabinet here in the lecture hall shows some of the components in the building of the mirror. The top right shows 3 to 4 kilo blocks of the E6 borosilicate glass that come from O'Hara Corporation in Japan. And in the middle, you see a cutout of the ceramic cores, which are used to make the mold. The ceramic core material is essentially what they use for the space shuttle shield. Each ceramic core is individually sized, it's numbered, and it has a specific position in the mold to create the parabola required for the GMT mirrors. Each core is firmly fastened to the floor of the furnace with those dark silicon carbide bolts. And then the process goes of melting and so on until the mirror is done. I'll talk about the top left there. Those are spreaders that are attached on the back of the flat surface of the mirror, hundreds of those, in order to implement the active optic system. This picture shows you in the top the 1-ton pots, they call them, of borosilicate glass that is made by O'Hara. And what they do with those, they chop them up, they break them up into those chunks of 3 or 4 kilo in size that you see in the lower left. Now, these pots of 1 ton of glass, the university is allotted 1 ton of glass from O'Hara each month. So they have to wait for 20 months in order to get enough glass to make one 8.4 meter mirror. So that's a couple of years added onto the process of making a GMT mirror. This picture shows the furnace area, the casting lab. When I was there, the top picture showed the furnace blank. The mirror had been made and moved, and it was in the process of waiting for the next activity. But the bottom right shows the mold being set. You see the outer rim of the mirror laid out, and there's the white ceramic cores going around there to provide protection for the edge. You see some of the 1700 ceramic hex cores starting to be laid out in the middle of the mirror, and around the outside rim of the mirror, there are steel bands to hold it all together. Once it's assembled with the ceramic core, the lid is put on, it's heated up and spun around to make sure that everything sets in place properly. And then it's opened up, and the workers get to work to put the glass blocks, 3,500 of them, individually over a course of a week or so on the surface of the hex cores. On the left, you see a fellow with glasses on, and what he's doing, he's checking the rainbow pattern in that block of glass to make sure that it's perfect and doesn't have any flaws in it. Now, this shows the furnace as it was the first time we visited in 2013. The lid has been brought over by a crane and put on over the mirror, and then it's heated up to 1200 degrees centigrade. Now, the melting point of the glass is 1050 centigrade. So once it heats up over the course of a week, the glass melts to the consistency of honey, and it flows over the entire surface, and it flows in between a gap left between each of those 1,700 or so hex cores. The spin casting, the turning of the furnace, is at a speed of about 45 miles per hour or 70 kilometers an hour on the outer edge. And the furnace is, when the furnace heats up, that entire 3-story area of the lab heats up to about 90 degrees centigrade. So you can just imagine how hot it is. Now, if you go to the Mirror website, you can see some pictures inside because they have cameras showing it melting and so on and so forth. They have to cool it down very gradually because they want the atomic structure to anneal and the atoms to interlock very tightly. That takes 90 days before the temperature comes down enough that they can open the furnace. Here the furnace is open. You can still see the hex cores in there, and a person's just cleaning that off. Oops. I want to say that the top and the bottom sheets of the mirror are only about 1 inch, maybe 2 inches thick near the edge, near the rim of glass. And in between the hex cores, there's a 1/2 inch gap. So there's 1/2 inch glass ribs connecting the top and bottom sheets. And yet that's still strong enough to withstand wind forces and gravitational forces as the telescope slews through the sky. The next order of business is to lift the mirror with the front surface and put it into a support structure that you see on the right. So the lifting structure has 36 pads. They're actually bonded to the front with something like bathtub caulking that you would use in your own bathroom. As a matter of fact, to remove those safely once it's in the support structure, an undergrad student suggested they use dental floss, and actually that's what they use to take the bonding adhesive off without harming the surface of the mirror. Here you see the support structures turned on its side, and an elevator structure is brought up behind it so technicians can remove all the carbide bolts. And then using power washers like the ones you buy in Home Depot, they clean out all the residue and they clean out the hex ceramic molds that are in each hole. And once that is done, then they can put plugs, rubber plugs, in each of those individual holes and take it to a grinding facility, and they grind that surface flat, perfectly flat. Once it's perfectly flat and completed on the rear, they can attach those 150 load spreaders that I showed in the earlier picture. And those are the individual actuators that manage the active support system for the large mirrors in the primary. Now, the final stage at the mirror lab is to go through something they called stress lap polishing. This picture was taken when we saw the LSST telescope mirror, the one for the Vera Rubin Observatory, being made, and it was being polished 24/7 at the time. In the back, and I have a close-up to show you, is the 48-inch diameter polisher. Each of those cylinders that you can see move tangentially to the mirror surface and grind off anything that the computer tells them needs to be ground off. This process takes a very long time, as you can see, with decreasing levels of grit until the accuracy of the mirror is down to 25 nanometers. This is a close-up of the large polisher you saw in the earlier picture. Now, during the polishing process, there are frequent checks made in the optical tower. Now, the optical tower, the bottom picture is looking up the tower, and the other picture was the back of segment 5 that was there when I visited a year ago. There's no way of having a crane in there. So to shuttle the mirror and its support structure back and forth, it's actually placed on a number of air carts, and they pump pressurized air in there so that it floats on that cushion. So essentially they're playing air hockey with these giant mirror segments. The test tower has a couple of large instruments in there. One is a laser interferometer you see on the left, and the other is a scanning pentaprism on the right, kind of simulating a star test on the mirror. Now, this image outside the lecture hall was an actual image of one of the mirrors, and it shows how accurate the grinding was. The green means that the surface is within tolerance, within the, this says 10 to 20, but they told us it was 25 nanometers tolerance. And the yellow means that it's still not meeting the tolerance level required. The tolerance level, that 25 nanometers, is like the size of a small virus, 1/5 of the size of the COVID-19 virus, or more practically, maybe 1/1000th the width of a human hair. They also had there a model of one of the 7 secondary mirrors that are used to reflect the primary back down to the instruments. There's 2 kinds of secondary mirror being constructed. One, the FSM, the fast steering one, will have active optics. It's out of a very rigid piece of glass that doesn't bend, doesn't flex, and all the optics do is tip or tilt based on the gravitational forces as the telescope slews through the sky. They may use that for certain observations, and they more likely would use it when it's too windy for the adaptive optics system. So that's the second one. And the mirror there is actually very, very thin, only a couple of millimeters thick, but it has hundreds of magnetically actuated pistons that deform the mirror depending on what the laser stars in the night sky tell it about the atmospheric turbulence and how it needs to be changed. So that would be going on each of the 7 adaptive optics mirrors. Now, when the mirror is completely done and ready to go, it's wrapped in a protective blue shield and then placed in this large container weighing a total of 55 tons. It's transported to a storage location near the Tucson airport, and it stays there until it's ready to be shipped to Chile. One mirror would be shipped at a time, just to protect the investment. Just the labor going into this, which is at the university's cost, no markup, that's about $2 million. Plus, there's about $23 million worth of glass in each 8.4 meter mirror. So it's shipped from Tucson down through Arizona and across Texas through the secondary roads, because the police would not let them go on the main highways. And in some cases, they said the clearance on either side of the mirror would only be 1 inch on the roadway. And it goes right down to Houston and loaded on a cargo ship. And on that cargo ship, it's actually welded to the side of the hull of the ship so that the ocean waves or storms, as it goes down through the ocean, the Panama Canal to Chile, it won't wreck the mirror, it won't get jostled or anything like that. And then it's trucked up the mountain, and then it's time for coat and quench. What I mean by that is each 8.4 meter mirror takes about the equivalent of 2/3 of a can of Coke of aluminum to coat it. So essentially, you could coat the mirror with a 6-pack and still have 1 can of Coke left to quench your thirst after you've done all that hard work. This slide shows, as of a year and a half ago, the mirrors that were cast already, 1 through 5. 1 and 2 are completed. I'm not sure whether 3 is completed yet, because they don't have data for 2019 and 2020, which was kind of slow, a special year. This year, they're going to start up early in the year and cast segment 6. And towards the end of the year, they plan to cast segment 7. It's not yet certain whether they'll do an 8th segment. It's not needed for the telescope, but it was originally planned to have something to swap out the off-axis mirrors so that they could do maintenance on those and minimize the downtime for the telescope. This slide shows you all the mirror castings that were done by the Mirror Lab over the course of the last 15 years. The blue ones being, of course, the Giant Magellan Telescope mirrors. If you were to visit, and if you can visit after COVID is over, I'd recommend it. It's a very interesting tour, an interesting facility, and lots to see in Arizona as well. I expect they will be working on the remaining mirrors for another 2 or 3 years, almost certainly. So you would be able to see some of that action. First light is planned for 2029. This is the artist's depiction of the GMT, the building there, and then the facility for coating the mirrors, etc., right behind it. And to its left is the small admin building. Off in the distance, you see a road leading to a higher peak. It's not in the artist's shot, but that's where the twin Magellan telescopes, each of those are 8.4 meters and made at this mirror lab. That's where they are in Las Campanas. It's possible that they will go live in 2026. I think there's a bit of rivalry with other large telescope manufacturers. They want to be the first. So with 4 mirrors, 3 on the off axis and the center mirror, all of those will be done. They may go live a few years earlier. And then we'll start to see some interesting results. This shows you here all the major telescope mirrors that exist or are being built around the world. On the top left is the Hale 200-inch that I talked about at the beginning. Down at the bottom left is the James Webb Telescope, and beside that, the Hubble Telescope. The Magellan Telescopes beside that, the Giant Magellan Telescope, almost the size of the Raptors basketball court in the bottom right. And the top, above that, on the right side, is the European Extremely Large Telescope, the ELT, and the 30-meter telescope. The ELT will also be in Chile, and the TMT will be on Hawaii. And actually, Canada is a partner in that telescope project. They will be larger than the GMT, but each telescope has its own special purposes, and in conjunction with the James Webb, we'll certainly have some interesting discoveries. Actually, this faint outline here is the previously overwhelmingly large telescope called the OWL that was abandoned by the Europeans. It was 100 meters, and current estimates would have placed the cost around $20 billion to build it. But this class of telescopes that I've been talking about, the GMT, TMT, and ELT, they're all in the billion-dollar class, so more affordable. Well, here we have the 3 telescopes that make up the new class of extremely large telescopes, the Super Bowl of telescopes, if you will, that are 3 times or larger than any current telescope. The ELT, in fact, is larger than the Roman Colosseum on the right. And you can see the GMT and TMT are very similar in size. So we look forward to lots of interesting science from those telescopes. If you're interested, I encourage you to go to the gmtobservatory.org website and check it out. There's an excellent science book that they produced in 2018 that's at the top that has lots of information on the instruments on the bottom right there that they have and the science that they will produce. Very exciting that we'll probably see results that will show whether there are biosignatures in the atmospheres of some exoplanets with these large telescopes. I forgot to mention, but you'll notice that all the telescopes are segmented, but the GMT are very large. So it has an advantage over the ELT and TMT, which have a very complex adaptive optics system. It's much simpler for the GMT. Still complex, and the most complex ever built so far, but more manageable. Plus, they have the largest possible telescope surface with a guaranteed curvature on the wave surface. So that's a definite advantage for the GMT. That's it. Thank you very much. And if there are questions, Blake, I'll be happy to take them.
Thank you very much, Bryon. That's certainly an engineering marvel. Amazing stuff. Let's go over to Blake. Any questions?
Yeah, thanks. Leo2 CAF asked the question regarding cooling and cracking. Let me find the question here. Back at the time of the casting of the large Pyrex mirrors like the DDO and the Palomar, cracking while they cooled was a problem. So he's asking, have the new materials and techniques overcome this? And I'm curious how.
It seems to have overcome it. With the Hale telescope, the mirror there, the first time it failed because one of the molds came loose and floated to the top. So actually that mirror is on display in the museum, and I've seen it there. If you want to go, you can see it there. What almost destroyed the final successful mirror was a once-in-a-century flood of the river below the factory that they had to sandbag and protect the mirror, which was in its cooling phase, and it would certainly have cracked if the water had reached it from the river. So as far as I know, they haven't had failures with the process they've been using at the University of Arizona.
Yeah, I guess with these bigger projects, they don't want failures.
Yeah, it's an advantage with the ELT and the TMT. The mirrors are all smaller, more manageable segments, but the trade-off is, of course, the computer control and adaptive optics are incredibly complex.
Mm-hmm. You had mentioned that the provider of the glass could only do so in like certain quantities. There was an allotment or some sort of restriction.
Right.
Why was that?
I don't know. It could be that the demand for optical quality glass was so great that they couldn't meet all the requirements, and they divvied it up between different universities and different companies that were requesting it. That's my guess as to what happened. I mean, a ton of glass is an awful lot. Yeah. I think some refractors use this kind of glass, and they're not using anywhere near a ton. That would make a lot of amateur astronomer refractors, that's for sure.
Very good. I have one more question from me, and that is, how much are these tours that you've been taking? Do you recall the prices?
I think they're maybe $15, and they're a nominal sum. The tour groups are limited, maybe 15. I'm not sure we had 20 people, but they were limited in size because of the close confines and the walkways that you went through. And they didn't want everyone going through there.
And how far in advance did you have to book? You obviously planned some trips around it.
Well, it depends. February is winter season, which is busy down there. I booked a few days in advance and was able to get on a tour.
Great. Okay, thanks a lot, Bryon.
Okay. Cute.
All right. Thanks again, Bryon.